Cosets and Lagrange Theorem. You're supposed to have seen this if you have taken abstract algebra or modern algebra. Okay. So the definition, let G be a group and H a subgroup of G. Okay. So when you are given a condition, you have to read and understand very clearly. Let G be a group, meaning you have identity, you have inverse, it's associative, and so on. Okay, close. H is subgroup of G. So you have remember in H is also close, there's identity in H. Okay, and then for A in G, so this is A is an element of G. It might not be in H. Oops. A can be outside, A can be inside. Okay. So A can be here, A can also be here. We don't know. A is in G. AH is A times H. Okay. H in H. The left coset of H in G. I think surely most of you, probably some of you are doing your PhD. So most probably you'll be a lecturer, right? Or teaching. And those who are just now doing master, you probably will continue for PhD. Not only you have to know the definition, you probably will have to teach this class, I don't know. So you have to start practicing saying it, okay? Not just memorizing the definition. It's like the left coset of H in G. English is like weird. It's hard. It's like Arabic is actually, if you speak Arabic, it's like Arabic. It changed a lot, right? So when you presented probably your viva, your defense, your proposal, you're taking master, you have to present also your dissertation, make sure you know what you will present. So you can practice reading it to yourself. HA is H times A. And this is, because A is on the right, so you say it's the right coset of H in G. Okay, and there is a dot here if the operation is plus. Okay, the operation is plus, then you put a plus. So there should be a plus here. And also on the right. Okay, so this is called the coset. And A, this A is the coset's representative. And one coset can have many representatives. It's not unique. Okay, you can have. We will see in a minute. Now, coset partition the group. Cosets partition the group. You know what partition means? You learn set theory, you know partition. So if there is a set, I call set, S, union of Si Okay. Partition means it's a union, and oops, before that it's not empty, and the intersection is empty. This is partition. It's like you have a cake. You have a cake, you cut the cake. That's partition. You don't cut the cake like twice, like you just cut the cake once. You can cut the cake evenly, or you give more to, say, Hassan, less to me. Okay, the uneven one. So this is the partition, yeah? Partition. Okay. So let's see. The first example, G is Z8. And H is subgroup of G generated by 2. So two, 4, 6, add, right? Is order 4. Okay. Now, this one, right? 8 of them. 8 of them. H is a subgroup, just 4 of them. So you want to see, you take one element here, that's A plus H. Okay, so if it is an identity, remember the formula? It's just H, right? So identity, if it becomes the representative, is all H. Okay, so 0 plus H is, you add 0 to here, is H. Okay, if you check with 2 plus H, if you see 2 plus H, okay, I cross this like this. Okay. Actually, if H is in H, sorry, I use a different, if X is in H, XH is H. Okay, so there is this. So this is equal to Y. Add 2 to H, add 2. You get 2, 4, 0, 6 plus 2, right? 6, 0, right? Add 2. 2, 4, 6, 0. Modulo 8. This is H, right? And then you can do 4 plus H. 4, 6, 0, 2. Again H. So all of this plus, they're all equal. So I can just write equal 2 plus H equal 4 plus H. Zero, 2, 4. One more, right? 6 plus H. Okay, now there's 1 plus H. So you add 1 to H. 1, 3, 5, 7. And this is equal to 3, 5, 7. For example, if you add 7, you get 7, 1, 3, 5. Okay, they're all same. So, meaning this group with this subgroup has only two cosets. Two cosets. And the cake is divided into two. And this is Z8. Right? This is the first coset with the first subgroup H. This is the second coset. Okay, don't say that you cannot add element with a subgroup. But this is coset, it's defined. Okay, it's defined. So you cannot say this is impossible because this is an element, this is a subgroup. No. For this case, it's okay because it's defined as a coset. Okay. You can now go to the next example when H. Okay. Before this, you can actually find the number of cosets. Number of cosets is the order of G order divide is the index of H in G. That is how you say it. It's a colon. It's a colon. Order, it's a colon. The index of H in G is the order of H. G divide the order of H. If it's finite, so this is 2. That is the Lagrange theorem. Okay. So example 7.2, you have 3 coset, Z9 and 3 coset. Now you can go to dihedral group or symmetric group. Okay. Lagrange theorem said that actually this is Lagrange theorem. That the order of H divide the order of G. Okay. The other way around is not true. Okay. The converse of Lagrange theorem is not true. Meaning, if K divides G, there is a subgroup of order K. That is not true. If H is a subgroup, the order has to divide the order of G. Okay. The converse means if the number divides the order of the group, there is a subgroup of that order. Not necessarily, right? Like in S4, there is no subgroup of order dividing S4. No subgroup of order 12 or 6. Okay. If the operation is multiplication, like example 7.3, okay, you have to do multiplication. This is easy because it's just addition. All right. No, it's raining. Okay, let me see. Number of coset. Okay. All right. So let me try one more. Let's see. For example, G is S4. And just now H is this. Okay. And the question is list all cosets of H in G. So The order of S4 is 4 factorial. The order of H is 4. So the number of coset is 6. Okay, so you need to list all 6 cosets. You have your notes, so you can list all elements in S4. First, you need to list this, right? So 6 of them. I just give you maybe 2, then you can try the rest. Okay, H. Just now, what is it? 1, 2, 3, 4. Then 4, 3, 2, 1, right? Is 1, 4, 3, 2. What's another one? Anna? This is to the 1, this is to the 2, and then to the 3. I just forgot this. 1, 1 to 2, ish. This is the inverse, right? 1, 3, 1, 3, 2, 4. Right, this, right? So this is all 4 of them. Is it? Okay. So you go to the next. You go to the next list. Okay, let me see. Go to page. Go to page. Example 411. I think is this the same thing? Page 53. S4, yeah? So S4, you go to the 24 elements and you cross out this. Cross out. Okay? So you go to the next 1, 2. 1, 2 is not here. So you go 1, 2, H. Okay, 1, 2, H. So you multiply. 1, 2 times this. 1, 2 times this. Okay, so 1, 1 to 2, 2 to the 1, gone. 2, 2 to 3, 3 to 4, 4 to 1, right? Next, 1, 2 times 1, 4, 3, 2. 1, 1 to 4, 43, right? And next, 1, 3. So 1, 1 to 3, 2, 4, right? Okay. So you have another 4. And then you go cross that page. Cross. Let me cross mine. The pencil. Okay, I cross out. I cross out 1, 1, 2, 3, 4, 1, 4, 3, 2, 1, 3, 2, 4. Where is 1, 3, 2, 4? Okay. Now I cross 1, 2, 2, 3, 4, 1, 4, 3, 1, 3, 2, 4. Next is 1, 3. Okay, next is 1, 3. Then you multiply. You get another 1. Okay. Then you look You have to have 6 of them. Okay, so yeah, you have to go through again 6. So this is how you have to go through. Multiply out, then cross, and take the next one that you haven't crossed. Then you cover all. So this is a cake where you divide into 6, and each one has 4 elements. Yeah, this is coset. Okay, you can do that yourself. Okay, now the next one you can read by yourself. Okay, properties of coset. The first one, properties of coset, what's the page number?
109.
109. Okay, properties of coset. The first one is the representative is always in the coset. You see this? There's always 1, 2 there. Because there is an identity, the identity is always in the subgroup. Properties of coset. A is always in AH. The proof is since H is a subgroup of G, EG is in H, A times E is A. So this is it. I can give you this as a question to prove. Prove that A is always in AH. Okay? And the proof is quite simple. This is the definition, right? This is the definition. Since H is a subgroup, E is always in H, or A times E is E. Okay, so you see that 1, 2 is always in here. The first one is always multiplying by the identity. Okay, the second one, if this is equal, that way, if it's in H, AH is H, like this one. This one. 1, 2, 3, 4 is in here. You multiply by this, you get this back. Okay, because H is a subgroup, right? H is a subgroup. If A is in H, A times H is again in H because it's close. Okay, and the other way around, if this is equal, if that is equal, then this A has to be inside. Otherwise, it will go out. The third one is two sets are equal, or the intersection is empty. If I give you a question in your second test, right, and you list the coset, you see the intersection, your answer is wrong. Okay, your coset is a partition. So make sure your coset are equal with this one, or they don't intersect. They don't intersect. Intersection is empty. If two coset are equal, to check whether two coset are equal or not, you can just take this inverse multiply by the representative. Because sometimes you're not sure whether these two are equal or not, so you just take one and multiply the inverse by the representative. Okay. In the next chapter, you will need this. Okay, next. How do you read this? Two cosets have the same order. or same size. Okay, you cannot be you cannot be unfair when you cut the cake. They're all the same size. Okay, so you have to have the same size. This is not necessarily true. This is next chapter. If this is true, we say that H is normal in G. So that's next chapter. I normally don't use this so much in this chapter, but if it's not abelian, this might not be true. Okay, you can try with the permutation. AH is not HA, but if it's a abelian group, then they are equal. Okay, and they are not necessarily a coset. Is not necessarily a subgroup. A coset is only a subgroup if A is in H. You remember just now we have Z8, this is Z8, Z8, and we have H order 4. We have only two cosets. One is H, the other one is not a subgroup because the identity is already in H. So H is the only subgroup with the coset, okay, for the element of H. Okay. Now, as assignment, we cannot be online for too long. Okay. This is reading assignment, yeah? Reading assignment. Go through the lemma given here and how to prove the lemma. Okay, I already mentioned just now some of them, but go through again how to prove this. These are all actually for this one. All right, so theorem 7.2, groups of prime order are cyclic. I think this one, there's a proof there. You need to insert the proof here, Hannah, this time. 7.2, the proof I asked, I think, in chapter 3, right? Groups of prime order is cyclic. Okay. You know the proof is quite easy. This is interesting. This is actually because of Lagrange theorem we have this. A to the order of G is E. How do you prove this? A to the order of G is always E. You know, if A is an element of G, the order of A always divide, right? Okay, always divide. What does it mean? There exists integer k such that k times the order of A is the order of G. So this implies A to the k times A is A to the order of A is k. This one is already identity. A to the order is identity. So that is why any element to the order of the power of the order of the group is E. So using the fact that the order of element divides the order of the group G. And you have to know what it means by divide, a factor of. That is integer, such that k times A is G. That's why we're saying that 4 divides 20, right? Because there is a 5. 4 times 5 is 20. Okay? I will stop here. I will continue on Wednesday on application of coset to permutation group. It's very simple. Okay? And then I will continue with a little bit of normalizer and centralizer. And then I go to normal subgroups and factor groups of chapter 8, right? And then there will be, wait, how come assignment is due Wednesday? It's okay, right? Although it's midterm break. There is no class next week, so assignment is still due next week because you can just send through online. Okay, and then after midterm break, then I will give you assignment chapter 7 and 8. Okay.